Jonathan Logan, thanks so much for joining me on this. I really appreciate it. I think I've read a tweet recently about the shutdown of crypto hippies, and
Yes.
I thought, this could be an interesting story, given that crypto hippies is like a privacy preserving network. And I thought, oh no, I got to get hold of you. Your name is obviously a pseudonym. Maybe you can tell us a little bit about yourself, that which you wish to share. And yeah, apologies for the lack of video, right?
Yeah, so the lack of video is all my fault because I simply don't like my face being recorded. So
That's
yeah,
cool,
what to
bro.
say about myself? That's
Don't
one
leak
of
any
those.
details.
No, it's more like do you select that is interesting and what isn't.
Well, I suppose,
So I also go under the name The Real Smuggler.
yeah.
Um, I've been in to the communication, privacy, and security field since 2000, I think,
Mm-hmm.
basically. Um, I mean, I ran a couple of relayers before that, like mixed master relayers and stuff like that. Um, yeah, I mean, it's hard to really pick what is of interest. I wrote a relatively famous little treatise, second round book on strategy. I'm something like an agorist, um, or post-agorist, actually.
Yeah.
Yeah, I don't know. So
So
it's hard to select what
no
people might be
problem, no
interested
problem. We can sort of narrow down on the interesting, no, many interesting things, I'm sure. But one of the things that really piques my interest at the moment is how you guys came about with crypto hippies. So maybe you can like sort of like go into that. Yeah, like what were the circumstances? Why did you guys spend so much time and energy, committed into
in.
building this? And then later on, I'd like to go into um, the set of problems that arose
Sure,
from it, and also architecture. So in
sure,
this podcast,
sure.
we can get raw details, so you can go really
Yeah, yeah, okay, okay,
really
okay.
nasty.
Okay, the story of Crypto Hippie probably starts in 2003, 2004.
Yeah.
And at that time, I'm I make my money by basically doing tech consulting over IRC on an anonymous IRC platform. So I basically spend my time in front of the computer and tell people how to administer Unix systems mostly. And that was a fun time. Um, and I actually made money of it, which is amazing when you think about it. Because back then it's like pre-Bitcoin times, right? And
Slackware.
well, no, we have more distros than just Slacker. But
Yeah.
the interesting thing is that there was this thing called Invisible IRC Project, which was an anonymous IRC hangout, and there were a lot of cypherpunks and a lot of people from the digital cold economy and stuff like that. And we had like an internal or multiple internal payment systems on that specific IRC server. And I basically answered questions, and then people gave me digital money for it. And so I lived on that place. And one of my repeat customers, so to speak, was an outfit called MetroPipe, which at that time ran proxies um, for privacy stuff. So mostly the usual SOX proxy here, HTTP proxy here, and if it got really wild, it would be SSH tunneling. And they then bought servers from me. So for a while, I operated like a server exchange where I would buy and sell servers, rent them out, administer them, etc. And so um, then they asked, hey, can we do more than what we've been doing so far, SSH, etc. And we decided on creating an open VPN hub. So it's, as far as I remember, I think it was the first one that was like sold on the open market as a privacy tool.
Mm.
And long story short, I operated that for a while, and then MetroPipe went under. So they had business problems. And one of the previous partners of MetroPipe reached out to me, and he wanted to set up its own system, and then that failed. But it basically triggered the idea with me to do it myself as a business. And then I was looking for the right person to do it with, because I'm really not a business person. I'm a tech person, but I suck when it comes to anything marketing and all these things. I'm really bad at that, like enormously bad. Basically, I do negative marketing, I think. And so I was looking for the right person, but also like the right mindset, because if you want to do something privacy related right, you're attracting heat. So it's not like any other business. It's something where you're basically taking over the heat that the client would otherwise get, and that is part of the deal. Basically, you're insulating the client, and you have to have a certain mentality for that, and you have to have certain values for that to work. And there was a dude that wrote a book, The Lodging of Wayfaring Man, which was a bestseller in the digital underground freedom whatever scene at that time. And he had published his book anonymously. And I de-anonymized him, reached out to him, and said, let's meet.
How did you de-anonymize him?
Stylometry. So I went over the statistics of his writing, and and then we met, and I think it was February 2007 or something like that. We met at a small hotel outside of Munich, had a few drinks, and basically talked about if we want to do something crazy. And Paul Rosenberg, who was the mysterious person, agreed. And I think half a year later, we had our system set up, like the initial version. I mean, we went through 4 versions of the whole system in our lifetime. And yeah, and then we began. And first it was relatively slow. Then we actually had a few very good years. And then we ended that with some very bad years. And then it all exploded. Oh no, imploded, not exploded, imploded. That's the story.
Okay, so yeah, I mean, you're sweeping a lot underneath the rug there. Like for example, what was the specific purpose of this? Was it to insulate other clients and provide them a platform for communications? What exactly is Crypto Hippies?
So our purpose was always to allow people to use the internet in privacy without having to give up too much of its functionality and comfort. So we wanted to have a fast system. We wanted a system that supported most protocols, that was relatively easy to install, but at the same time would provide a realistic privacy shield for them.
Right.
And with realistic, I mean, it always depends on your threat model, right? So it's not that we protected people against the NSA or something like that. It's more like local government level plus normal data collection companies. So that's it. And we basically only focused on traffic anonymization. So we didn't go beyond that. So we didn't create our own browser to do cookie management or anything like that. So it was just, in a sense, it was a very advanced VPN service, plus a few, how do you call it, convenience services. So we had our own mail server, which had stuff like header scrubbing and all those basic tools for making privacy a little bit more achievable with email. Wide alias support, so you could create an alias for basically every sign up you would do. We had an XMPP server for chatting. We had some cloud storage for people, and so basically the minimum pack of what people would require on the internet these days. The minimum services you would expect, and we basically combined that into one bundle, and yeah, that's it.
Okay, all right, and all right, and I mean, you had a number of customers that was paying for all the services for a period of time, and then it dropped off. Why do you think it dropped off?
Oh, there are a lot of reasons for that. I would, to a certain degree, it has to do with two major issues. And issue number one is what's the sustainable market for privacy services? And VPNs are not purely privacy tools. So there's a lot of additional use cases to public VPN proxies. And the most important one is circumventing geo IP locks. So being able to consume media from different jurisdictions. And that is by far the biggest use case for most people of using VPN services. And since we had a very strict privacy first policy, our service was actually not good for that. So in the competition to services that had a focus more on the demand to circumvent geo-blocking, we lost out in the competition. So that is one major reason. The other major reason is that we had a very idealistic targeting of people, targeted older non-tech people as the focus of our marketing, and that was really bad. So that is that basically broke our neck doing that, because it creates the most expensive customers you can have, and they have the tendency to die off.
Yeah, that tends to happen with the older demographics. Yeah.
Yeah. So I mean, it was really like, it was an idealistic decision. It was this, hey, our service is easy enough to use for
grandma
people that are not tech savvy. So, and then you have grandma. But the problem with grandma is grandma needs a lot of support, and grandma really likes to talk. And then you waste a lot of time on support, but their life story afterwards. So,
oh, go on.
So that was, and sounds funny, but it actually means that the main cost of operating such a service, other than legal, is support staff.
Yeah.
And you can waste a lot of money on support staff.
Mm-hmm.
And yeah.
Yeah. And so I'm also going to be doing a little bit of a devil's advocate questions
Sure,
on behalf of maybe the audience, what they're thinking. Like, for
sure.
example, why is VPN not enough for privacy preserving internet usage?
Well, if it's not enough, if it's enough, that really depends on your threat model. You
Yeah,
know, so
okay.
it's not a binary question and not a binary answer. So,
So how does one look
but
at it then? How does one assess this
yes,
situation?
yes. So, um, for a normal internet user, it is not enough for the simple reason that you're using a stack of technologies, and the whole stack has privacy issues at some point. So let's imagine that you're using a web browser and you're connecting with your web browser to some website. You log in with your real name, but while you're doing that, somebody serves you an ad and puts a tracking cookie for that ad on your computer. And basically, what happens is that in the background, there's two unique identifiers that are going to be connected. That is your account at the website itself and the tracking cookie for the ad network. And then you go to a different website and you log in with your pseudonym. But the website is using the same ad network or the same ad broker or whatever. And then it will connect those two unique identifiers again. So, and that is something that is non-trivial to battle. So one of the things we did there is we did a lot of DNS blocking. So we would block ad sources, tracker sources, etc., directly on the DNS level. And if they were using unique infrastructure, we would also do that on the IP level. That is how you can suppress a lot of it, but it's not. There's no guarantee to that. You know, you have to catch up with how their infrastructure is set up, who's on the market, etc. And in that catch-up time, you will always have leakage. Plus, there are simply things that you'll miss forever. So that is just one example why just VPN is not enough. There are other things. There are things like browser fingerprinting. There are things like the TCP/IP stack fingerprinting. I mean, what we did there is we never did anything against browser fingerprinting because that was completely outside of our abilities. But what we did, for example, is we would transparently take over TCP connections on the VPN and run them through our own stack, basically. So to drop all fingerprinting abilities on the TCP stack. But the problem with that is each one of those techniques that you apply, and you can do similar things to UDP, so there are UDP fingerprinting methods. If you do that, you're degrading the network to a certain degree. Because a lot of the hacks that software is using don't work anymore. And it's those hacks that often make the difference between your videos play fluidly or they stop every 10 seconds for half a second.
Buffering.
So,
Yeah.
yeah, exactly. So, but as I said, you know, you have more fingerprinting abilities. You have TCP fingerprinting, UDP fingerprinting. You have latency fingerprinting. You have page call order fingerprinting. You have e-tag fingerprinting. You have cookies. You have browser fingerprinting. So there are probably 1,000 ways to create links between your communication targets and you. So basically, make a guess if you're the same person on two different sites, and if you then don't have the right behavior because you're not using pseudonyms to log in, but your real names, etc., then you are effed. So it always requires this very. In the end, you really have to be aware of what you're doing, and just using a VPN will not create a magic protection. In the end, you have to behave in a certain way. You might have to use different browsers on your machine and stuff like that.
Right. Yes. Yeah. Yeah. It is. This rabbit hole goes pretty deep. But then some might also say, how about just using Tor? I mean, Tor is the condom of the internet, right? Would you
Well,
agree
it
with
is the
that?
condom.
Would you
Yeah.
agree with that?
Well, as I said before, it really has to do a little bit with for what use cases you need privacy for. The goal at CryptoHippie was to make privacy protection a little bit invisible for the user. So you can use the internet as you did before. You can use basically every service, etc. Doing that through Tor is a hell lot more complicated because there's a necessary limit to the bandwidth that you can get through Tor. There's a necessary unpredictability of how much bandwidth that you can get through and how your latency looks like. There is a necessary limit on what services you can reach through Tor, because Tor exit nodes have to protect themselves as well. So there's all of that, of course. And then on top of that is the question of how you do your trust calculations. So when we started, I think, before Snowden even, if I remember correctly. And before Snowden, people really believed that you go through a proxy, you go through Tor, and everything is fine because nobody cares. But the problem is that some people really care of getting their hands on all kinds of data. And that in the context of Tor means that there are continuous attempts to siphon as many data out of Tor as possible. And because Tor essentially is run by anonymous parties, that is relatively easy to do. So the thing that you're risking as an attacker on Tor is that you have to set up new nodes, but you'll not leak that you're the NSA or something like that. And there's a lot of things you can get out of Tor even without being a dramatically big attacker. So especially before HTTPS became the standard for 99.9% of all websites, a lot of Tor exit traffic was basically captured. Let's see what people are communicating. And there's actually a famous leak from Scandinavia where a Tor exit node got their hold on a lot of diplomatic documents because they were communicated through Tor. And they basically took that off the traffic. And then there are more active attacks you can run as a Tor exit node provider. You can try to strip SSL. You can try to force people to not use SSL or to use SSL with an untrustworthy party. That happens quite a lot. And if you're good at it, it's extremely hard to detect, actually. And there have been enough cases of basically all SSL traffic being replaced, like being proxied by using valid certificates from corrupted CAs. And I mean, the good thing is that browsers are catching up on attacks like that by now. So you have stuff like certificate transparency in Chrome that makes those attacks harder. But for a while, that was exactly what was happening a lot on Tor. And essentially what you have is this playground for everybody who wants to try their hands at getting data, and that is Tor. So that's like the other side of Tor. It's great for playing around with those things. That doesn't mean that Tor is not also a good service, but similar to VPN, it really depends on your threat model, on a realistic assumption on how your behavior, on what your behavior is, what your goals are, to make the decision of what is the best use for you at this moment for this specific task. So I'm always a little bit skeptical when anybody comes around and says, okay, whatever, our VPN is the solution for everything. Or equally, Tor is the solution for everything. Neither is true. And that is one of the issues of internet privacy in general, is to actually do it well, you have to understand what you're doing. And people don't. People don't understand what they're doing. And even a lot of technical people really don't understand what they're doing there. They don't understand the complexity of the problem. And so what we're really doing is we're shifting probabilities a little bit, but not decisively, I would have to say.
Okay. So you mentioned CAs. And actually, CAs form a pivotal part of I suppose the security of the internet. Maybe do you want to go into like the reason why CAs are problematic from a security stance?
Sure. Well, I wouldn't say problematic.
Can be problematic. Sorry.
They can be problematic. Exactly. So CA stands for Certificate Authority, and the use case that we have on the internet in most cases is X509, which is what is the design of public key infrastructure that is underpinning most of our transport layer security. So when you see a green lock in your browser location bar, that usually says that you're using TLS or SSL. I mean, the modern protocol is TLS. And how that works is that your browser makes a connection to a remote server. The remote server returns its own public key, and it returns a signed version of the public key, a signature on this public key that is created by a trusted third party. And that signature links the address of the website to the public key of the website. And given these three sets of data, so the signature that does the linking, the address, and the public key, the browser can initiate a key agreement, essentially, sharing a private key between the website and the browser itself. And that private key allows you to communicate privately, right? And the way the browser trusts the remote website is by that signature by a certificate authority. And certificate authorities have a very interesting position, actually, because bigger public CAs have their own public signing key built into operating systems and web browsers, etc. And that is basically the way to print money on the internet, because everybody needs a certificate for secure communication. And until Let's Encrypt and similar services came around, having a CA certificate widely distributed meant that you'll never have to work again. And the problem with that scheme is that it requires all the certificate authorities that are built into your system, into your browser or operating system, to be trustworthy, and in two senses trustworthy. So they have to be trustworthy in how they operate, and they have to be trustworthy in the sense of being honest. So honest means that they would have a definition on how they identify their customers and issue certificates, and then they would also have to stick to those rules. And then the second question is, will they be able to actually protect their infrastructure so that nobody can circumvent those issuing rules? And the problem is that it is really hard to protect a bag of gold. And even huge and very important certificate authorities have been attacked in the past, successfully attacked in the past. And that has led to bad certificates being issued. So in the worst case, CAs have issued so-called subsigner certificates without domain limit, which basically allowed everybody else to become a CA as well, and create certificates for every possible scenario. And in the smaller cases, it just has been issuing secondary certificates for stuff. And that can be a real issue. It's not just an issue for your browser communication or your email communication. It can also be an issue, for example, for the automatic update in your computer. So if people remember Stuxnet and Google, they were actually using stolen, not falsely issued, but stolen certificates to slip in backdoors through the update process of your operating system. And so that is the general issue behind how we do public key infrastructure, or how we did, because there's a change to that. So what is happening today are two main things. Number one is that Google is operating this thing called Certificate Authority, which makes it much easier to find duplicate issued certificates, and that can be an indicator of attack. And the second thing that is happening is that we're beginning to, instead of using CAs, we're using the DNS system as a root of trust. So you can, instead of having a signature from a certificate authority, you basically put your certificate into the DNS system, and you activate DNSSEC, and then you can basically deliver proof of authenticity over the DNS system, and have the big hope that the DNSSEC stack is well managed. And if it's not, we're all doomed and we're all gonna die.
So yeah, like Dan Kaminsky showed quite a while back that DNS systems are quite vulnerable to attack. What makes you it's a bit of a fluke. What's the probability of this DNSSEC system standing up to attack?
Well, there are like three major issues with that. So number one is that registrars can still create a scenario in which domain owners can be tricked into using DNSSEC incorrectly. So that is there's this thing at the end of life for domains, where you can basically replace the keys in a domain with the right timing nobody notices. So it's kind of complicated and not very likely, because it basically can only happen like once a year or something like that. But it's still, and if you renew your domain early enough, you won't be. So that is an issue. Then there's the issue that, quite frankly, most people are not managing DNSSEC themselves, but they outsource it to their DNS providers. So, and you can still hack DNS providers and change everything you want there. And especially key rotation, doing key rotation correctly is a major nuisance on DNSSEC, and it frequently goes wrong. And that also means that a lot of ISPs, etc., and a lot of operating systems and browsers, etc., are not really willing to to make DNS a hard requirement for security, which means that if the DNS records are wrong, you might not get the correct error message that says, "Hey, there's an attack going on." So that is a little bit of an issue. So on the client side, there's still too much noise on that system to actually use it as a reliable source of trust. And then, of course, there's the signing hierarchy itself, which I mean, we have those big ceremonies for key rotation, etc. there, and they're not very frequent, and they're actually done by people that really know what they're doing. I would assume that if those ceremonies have been attacked, we probably have bigger issues as well. We might actually have and not know about it. So yeah.
That would be problematic indeed. The ghosts are walking through the system and we have no idea which is happening.
Yeah, I'm kind of thinking like if the DNS key ceremonies have been undermined, then similar things would be probably true for nuclear weapons, etc. It's the security standards applied there are very close. They're not the same, but they're close when it comes to complexity of attack. So I like to sometimes preserve this this last grain of naivete to be able to enjoy the world.
The human nature, and like, no, somebody will stop somebody from pressing the nuke launch button,
exactly.
right?
Exactly.
And it has happened a number of times in history, right?
Yeah, exactly.
Now, Jonathan, so okay, basically we're sort of covering like the general areas of the specific problems that going and doing a bit of a dive into each one of these things. Are there any other areas within the current infrastructure of the internet that you feel like, should be sort of mentioned or spoken about, or something that sort of nags upon you and like, God damn it, like, is there anything like along these lines that you think of?
That's a very broad question.
I know. I was just the first thing that sort of comes to your mind, the first nagging thing, because I want to open up a new chapter.
I have three
of questions.
things.
Go for it.
I think I have three things. So number one is, let's be honest, all our software sucks. So software security is a dramatic problem, and it's everywhere. It's from your PC to everything. There's no exception to it. It's just as it is, and you will never have privacy if there's no security. So the thing in digital privacy is you have to have trustworthy systems somewhere. They have to adhere to protocol, and they have to keep secrets. And if those systems are broken, they won't do that. And no matter of how great your white paper is on what could be built and whatever, if the implementation doesn't do it, you're doomed. And so that is something that always should be kept in mind, because in the end, it's somebody has to write that stuff, somebody has to maintain that stuff. If there's too much belief in the perfection of technology, you're missing the big point, and that is that in the end, everything is held together by people. And it's people that every day spend hundreds of thousands of hours to keep something like the internet running. And if those people would stop working for half a day, there would be no internet. And that is something that has to be kept in mind. And then there's another thing that I really hate, that is actually not about the shortcomings of the internet, but about people saying what the shortcomings of the internet are. Because they're like, for years, people are running around saying, oh, we have to change the architecture of the internet. Quite frankly, I'd never heard a good argument there. I think that a lot of people running around because they have no fucking clue how the internet actually works. and never worked actually at an ISP or anything. They've never actually read, TCP/IP stack specifications or anything like that. So, I mean, yeah, of course, there are like 1,000 implementation problems that have been overcome and will be overcome. It's people that fix that stuff all the time, but you can fix a lot of things without fundamentally changing the infrastructure. There's one single thing that I think is a shortcoming of the overall internet infrastructure or architecture. And that's in being able to have reverse route assurance and communicating the will to be a destination of traffic back to the source. So let me explain. So if you're on the internet today, depending on how good your ISP is, you are able to fake your source IP address. So on every internet communication, you have the source IP and the destination IP address. And it doesn't matter what protocol you use, those two things are always there. And reverse route assurance basically means that if you get a package, you would know that the source IP address is not falsified. So you would know that if you send a package back to that IP address, it is going back to the same organization, basically. Not necessarily the same computer, but it's going back to the same organization. And that is something that is really required to deal with denial of service attacks. And the second thing that you kind of want to have is you as a destination of traffic, you would like to tell every hop between the sender and you as a receiver if you don't want to receive the traffic anymore. And that the reason for that, again, is to battle denial of service attacks. And that is a feature that is in general completely missing because it is dramatically hard to implement and it requires a few other things to be implemented first that we're still working on. So for example, resource PKIs are things that are required for that. They are in progress and they will solve a lot of other issues. So for example, routing falsification will be a thing of the past in a couple of years because all routing updates will be signed. But that just takes a while to be rolled out because a lot of companies out there, a lot of countries are not necessarily on the bleeding edge when it comes to running their infrastructure, which is fine. It's part of how the internet works.
Yeah, that was actually, you just helped me a lot there with specifically being able to I am going against your perceived, your attitude. Like you mentioned on point number 2 is like those people that like go and create new internets and stuff like that. They don't know anything. Well, yeah, I'm doing that.
Why?
And, no, we can get into it later. But I'd rather get rid of the emotional charge first, and then. But the point, the 2 points that you just mentioned, they're like actually very useful for me. So thank you for that. But you mentioned 3 points. You said the first one is software shit. The second one is a bunch of guys going out there and creating stuff and they don't understand what they're doing. What was the third one?
The third one was the reverse route authentication.
The reverse route. Okay.
Being able to communicate things back, how bad it is.
Okay. Yeah. Oh, I mean, okay, we can go into each one of those things like massively. Like, fuck. Even the first one just makes me quake in my boots. Just how shit it is. I don't even want to go into that cesspit. But okay, so I'm going to open up the next chapter of questions, which is okay.
Okay.
So, Jonathan, if you were to have some sort of a magic wand, and go back to the 1960s and 70s when these packet switching networks were being created. With the knowledge that you have now, what concepts, remember, like, for example, some programming languages, they introduce a language concept or a paradigm or something, which removes not just a bug by itself, but an entire class of bugs.
Yes.
Right.
Yes.
So what concept would you introduce to those guys back in the 60s and 70s and 80s and say, okay, we need to have this, and it's going to remove an entire class of bugs and problems?
Yeah. I actually think that the most meaningful thing to change, and still to change actually, is the size of addresses. A lot of our security work is about establishing a link between a cryptographic key and an address, and projecting trust on that link. And the main reason why that happens is because you cannot use the cryptographic signifier directly as an address.
Dude, I'm about to give you a sloppy kiss, man. I'm about to give you a sloppy kiss. You better watch out.
So what I would probably do is, it's unrealistic, because in the 60s, a lot of the choices that they made were based on limitations of hardware. So there were things that you couldn't have done back then. And even today, going from 128 bits IP version 6 to 256 bits, which would be really nice, is probably something that would cause dramatic issues on the internet. And the other thing that you still haven't solved with that is routing complexity. So the issue with cryptographic addressing is routing. So, and that means for me that while that would be really nice to have, it would have been completely unrealistic to do it in the 60s. And it might actually be unrealistic to do on a large scale today. Maybe, 3-4 more cycles, and then we can do it. But the problem is that also requires replacing a lot of capital that is there. So a little bit of a Cisco router, a little bit of a Juniper router. You basically have like a sports car standing there, and you don't want to replace that every year. You're really happy when your router makes it for 10 years, And so realistically, while I would love those things, they would have required a different history. So there's no real thing where I would say we should have done that completely different, because a lot of the learnings that we made in between, a lot of the things that we developed in between were dependent on those initial choices. And those initial choices might actually have been what saved our ass. Perfection is usually not a good idea. Perfection is something that usually bites you in the ass, because perfection doesn't give you wiggle room. And wiggle room is really what you need to progress. You need things to break to be able to progress.
Yeah, indeed. Which there's a saying like human beings advance either with like war or like famine or something like that. Only big catastrophes cause human beings to advance. Now, it's very interesting that you brought up making cryptographic keys addressable, and then you immediately went on to the routing issue of this.
Yeah.
What the thing I'm working on actually does make cryptographic keys addressable. So it's like that information. I'm just with that information alone, that your public key, the network routes the packets based on this information.
Yeah.
And but just by having virtue of the key, I can ensure the strong privacy, strong security associated with it. And as you rightly mentioned, routing is a bitch. Routing is a bitch. I'm looking at it from a point of using Bayes' algorithm. So it's got Bayes has got a strong history in being able to find where something is not.
Yeah.
And from there, you can sort of narrow it down to where it would be. People have found like sunken ships or massive doubloons, the gold doubloons at the bottom of an ocean by using Bayes' algorithm. So, if you've got a distributed network of homogeneous nodes that all run this Bayes' algorithm, and information passes through, and they can actually start to train their Bayes algorithm to determine where is the best place to forward this type of request in future. So Well,
the interesting thing is there have been like I don't know, two dozen attempts on how to do cryptographic routing, and or using cryptographic keys as addresses in routing. And the issue is that it always requires a form of mapping, because the topology of your network and the semantics of your key have nothing to do with each other. And that is different on the internet. On the internet, there's a close link between address and topology. And that makes it very, very efficient to route things on the internet because of that link. So you have a structure in the addressing, and you have a structure in the how routing information is distributed in the network. So on the internet, you don't distribute routing information to every node, because you don't have to. But instead, what you do is you only distribute it to the edges, to the edge routers, basically. Those are the ones that really, really need it. They have to connect the various networks within the internet, because the internet is a network of networks. And the funny thing is that a lot of the information that is distributed there is actually not just a technical protocol, but it's a reflection of relationships between people and organizations. So there's a very human and a very economic layer to how the internet is actually interconnected, and that allows certain optimizations, and it allows a certain resilience, etc., that a purely technical system can hardly replicate, because there's this. I always say that humans are the thing that keeps the world from going into chaos. So we're anti-entropy machines, and it's the humans in the loop that take out the entropy there, and that is something that is really hard to replicate with code alone. And then again, you have the topology issue. You don't have a semantic in your keys that maps to the topology of your network. Then you have to create a mapping that creates this artificial topology and makes it findable. That is what addressing is about. And the efficiency of those systems everything we can do there has at least quadratic complexity. And if you look at the size of the internet today, we cannot do quadratic complexity routing on the internet, because we simply don't have enough processing power for that, and not enough bandwidth, because the most efficient routing algorithms are quadratic as well. if you cannot use the topology yourself. So that is an issue. So unless there's a great breakthrough in the future, which hopefully will exist, I think that these systems will necessarily have to stay within a couple of thousand or 100,000 nodes. They're not a real replacement to what we have on the internet, which they don't have to be. That's another thing. I think that what people often underestimate is that you can build secure things on top of insecure infrastructure. And you can even break a lot of base assumptions about the internet and still have a working system. So we do that all the time. TCP is actually something that breaks the base assumption of the internet. So instead of treating communication as packet switched, we're suddenly having streams, and yes, they're expensively simulated, but in a way they go against the grain of what the nature of the system really is, and they still work dramatically good, and we even improved on top of TCP and created additional protocols that are dramatically better than TCP. And what I actually think is that we have to learn one more thing, and that is that the addressing and the physical distribution of the internet is not really a limiting factor. It is just a substrate on which we build. And we can introduce very different notions there. So for example, what I'm considering the future of the internet to a large degree, at least for a lot of applications, because in the end, it's always about applications. I actually think that public message broker infrastructures will dramatically change how we are using the internet. I think that there will be a point where we overcome the whole model behind HTTP and go from a client server connection based whatever internet to something more of let's say a data driven internet, where
expand on that to the best you can.
Yes, it's a hard thing to explain.
Of course, I know.
So today, more or less, all models are about you wanting some form of information, and you go to the place where the information is, which might be very far away, and you tell that place to send you back the information. And that sounds very logical. But if you multiply that by 100 million, that's not as logical anymore. You have 100 million connections all going to more or less the same destination, saying, give me that kind of information. And what you could do instead is you could make the information travel towards you. Let's say that you and me would both be in Hong Kong right now. And you would make a request to Google for a certain kind of information. And instead of that information being just available to you, it would actually travel towards the edge. And if I make the same request, the information is served from the edge.
Right.
And the same thing is if you and I then want to communicate via Google, we might not have to go through Google directly, like have this whole link to the data center in Singapore, but instead the traffic would find a route closer to home.
Right.
And I'm not talking about peer-to-peer here. What I'm talking about is distributed messaging infrastructures, which have this ability to communicate interest through the network and route messages based on interest and allow things like subscribing to interest, etc. And since most data that humans communicate and use, like 99 point something% of all data, is not unique data. It is data that a shitload of other people are interested in as well.
Yeah.
And there's the and that is a change from how the internet was used in the beginning and how for what it was built in the beginning. So the initial use of the internet is really about these unique data streams that where data is communicated that is not, or where interest in that data is not a common thing. But today that is not true anymore, because the internet to a large degree is a consumer good, and we consume the same data. And that means that it is far more interesting to bring the data to the edge based on interest. And you can even do things like interest modeling. You can route by interest. You can make assumptions about interest indicators that you receive from certain nodes in the network and make predictions over who else in the network and where else in the network that interest might come up. And that is where I think where a lot of the future of the internet will be. So instead of considering it as a request-driven system of communication, it will be more like an interest-driven network of communication. And we already see that. So I mean,
CDNs.
CDNs is an example for it, but it's not a very good one, I think.
It isn't,
because they aren't interest routed. But a good example are push messages that you get. So what you do when you install an app on your phone is you're communicating interest, and you become part of an interest addressing system where the data already knows where it has to flow because you already communicated interest. So there's no request in the background all the time saying, hey, give me new information, give me new information, give me new information. But instead, there's one communication that says, I'm interested. And every other push message afterwards is a response to that first initial demonstration of interest. Yeah.
Okay, so I might be detecting a conflation of two things which might be incompatible with each other, and give me a moment to try to explain this. So, is there an element of pub sub going on there? So, you would subscribe to certain topics, and then from then on out, that messaging hub would keep forwarding that tagged interest data to you, and then you would unsubscribe when you're no longer interested. Is that correct?
Yes.
Okay. And then the second one is you were speaking about information-centric networking. So information-centric networking means that, okay, to expand the explanation a little bit, if you imagine the internet as an hourglass, there's the sand in the hourglass and you turn it around, then there's the narrow waist, right? The narrow waist at the moment on this current internet is IP. And everything below, at the bottom of the narrow waist, both sides of the hourglass see IP. The applications need to see IP. The infrastructure that moves the data needs to see IP. So the bottom side of this internet is all that which moves the data. And on top of the hourglass is all that which actually uses the data. So it would be in the form of email browsers, et cetera, would be on top of the hourglass. That explanation might be a little bit, I think you can get it though. But the point is that both sides see the IP address. By using information-centric networking, we actually shift the narrow waist to be essentially the cryptographic hash, the cryptographic public key.
No, it doesn't have to. It doesn't have to. No, it doesn't have to. So there's no cryptography so far that got into the system at all. So when you're thinking data-driven networking,
Be the name of the
cryptography
data.
is well, not even the name of the data. The only thing that really matters is the authenticity of the data at some point.
Well, you
And
need
the
crypto for that.
authenticity, yes, you need, but you don't need that for anything until you already have the data in your hand.
True.
So,
Fair. Yes.
so it is basically an after the fact authentication that you can do. And if you are really concerned about attacks on that system, because of this fan out effect that you have everywhere, it's very efficient to do the authenticity verification on every step of the way. Because you have a use multiplier, because there's a
Yes.
fan out on the end, you always have a use multiplier. So it really makes sense to make authenticity verification part of every single hop
Yes.
through which the data travels.
Hmm.
And you basically stop bullshit data at the source doing that. Well, not bullshit data, but
bullshit data.
falsified authenticity. So you can basically, it's not routing, it's filtering.
Yes.
It's like, and there are actually interesting possibilities there, because we're talking, for example, a lot about blockchains, right? And the interesting thing with blockchains is blockchains are probably the most inefficient database ever created. And they are basically completely useless with one exception. And that is unique mappings of authenticity. That's the one thing where you actually need a blockchain. So everything else, you better do somehow else. But for that, blockchains are the perfect solution, but they don't scale. But the thing is, you don't have to scale them as much anymore if you have this filter at the source approach. Because it's mostly a read-oriented and repetition-oriented use case. And so it basically would allow you to introduce your proof of authenticity once, and then it could be easily reused again and again and again, without actually increasing the load of the blockchain, basically. So you would probably end up with a system that did whatever 100 billion transactions total in its own lifetime, its whole lifetime, and that is not that much. That is something we can manage. And yeah, so an interesting thing to look at, just as an example, because there's a company that's actually playing around with public message-based infrastructures, and that is Syndia.com. They have this
spell them, please. Symbian.
Syndia, and since I'm not really good at keeping names, I shall better look that quickly up. It's spelled SYNADIA.com.
Yeah, okay.
Synadia, so Synadia.com. So, and they have an offering that's called NGS, which I think stands for Nets Global Services, which is this publicly subscribable message broker infrastructure. And it allows you to do things like, of course, communicate with your own devices without having to know where they are, etc. You don't need net punching anymore, because it's you're basically becoming client to a distributed infrastructure. And all the routing is interest-based, it's publish subscribe. So, but it has this interesting feature that allows isolation between domains. It's multi-tenant capable, but it also allows you cross-tenant communication by basically offering your data to other clients. And that is a highly interesting way of looking at a lot of communication. So yeah.
I didn't know that. I'll have a look at that. Yeah, nat punching is something I've been thinking a lot about. This protocol of that I've been working on. It's not as easy as it as some people might say.
I am aware. Yes. I heard about that problem. Yeah.
Oh, just offhandedly,
Exactly.
Yeah. Um, so now, did you ever think about? Okay, so during the design of crypto hippie, did you ever think about going off into these more uh, non-run-of-the-mill protocols in order to do this, or has it always ever been to make sure that it's just bog standard services on the internet to give people access to bog standard services on the internet while being secure? Or have you ever thought about going off into these other sorts of protocols?
Um, no, and there's a reason for that. So the topology of your network has strong implications on privacy. And for privacy preserving systems, there are basically two approaches you can make. You can create a peer-to-peer network, or you can create a funnel network, and or a centralized network. Let's be easy to be in the beginning. So a centralized network, and those are like the two almost ideological choices that you make there. But they are based on two ways on looking at the privacy problem. So the peer-to-peer approach is based on observability of links. So it makes the assumption that an attacker cannot observe all links. So you increase the number of links. And the funnel approach, or the centralized approach, is based on the assumption that the attacker cannot distinguish communication. So those are the two different ways of looking at privacy. And just to explain, the distinguished part is you have two messages coming into a black box, and you have two messages coming out, and you being able to, as an observer, to say which message that came out is connected to which message coming in. That is the question of distinguishability. So, and if you don't trust the black box, you just put multiple black boxes behind each other that are from a different trust domain. They're operated differently by different people, run different software, etc., etc., but adhere to basically the same protocol. And that, so the latter part, like the centralized black boxes, there's an upside to that. The upside to that is they are not just very efficient, but they're also provable. So no matter what assumptions you make about the attacker, you can create a system that does not leak information that leads to distinguishability. So you can build a system where you can make a very well-reasoned argument about how private that system is. Because all the information to actually make that judgment is contained within the system. So it's contained in the protocol, and it's contained in the operators. So you can make that judgment. On a peer-to-peer network, you cannot. So if your assumption on a peer-to-peer network is the multiplication of links, then you're making an assumption that is actually unprovable, and that is the unobservability of links. And to be exact, we already know that it's a false assumption, because the observability of links is latest since Snowden. We should know that that is what it's all about. It's observing links. And if you are working in internet networking industry, you actually know already that all links are seen, because we have stuff like trading net flow information, because it's a relatively important thing to battle denial of service attacks and other kinds of cyber attacks. So there's a global market on trading net flow tuples. So that basically means that with the exception of edge links, like ISP to individual customer, more or less all other net flows are publicly available. And that includes all infrastructure you could build to build a privacy preserving system. Hence, the assumption of going on unobservability of links is a false assumption. It's actually one of the critique one could leverage against something like Tor, is because it has too many nodes, it makes it insecure. Because the question of indistinguishability becomes weaker and weaker the more you spread traffic out over links. So what you really want is you want as much traffic going into your black box as possible, because it increases the set of alternative outgoing messages. It's so basically you increase the anonymity set, and especially because privacy is a multi-round game, that makes a real difference. Because things like the simple question of are you online or are you not online can take this momentary anonymity set and cut it in half. And then you repeat that again and you cut it in half. And you repeat it again and you cut it in half. So most systems actually in reality do not provide you multi-round privacy, because after latest a week, you become statistically distinguishable. And so it makes a lot of sense to have this huge anonymity set that spans across those on-off times. You know, your anonymity set has to be big enough that it covers your time of sleeping, basically. I mean, it's less of an issue today because it becomes feasible to create always online systems, but or it becomes more feasible. It's not really feasible, more feasible. But so that is the reason why. Long explanation short again. That's the reason why we haven't chosen a lot of the more arcane academic protocols, because the science of anonymity is actually well established. So it's not something that we don't know how it works. We know how it works since the 80s. So to be very exact, we actually know the theory behind it since Shannon. You know, so and you take that and you apply that, and then you become depressed. And then we go into the 80s, and then we figure out that there are things like mixed networks. And since the 80s, there's only one thing we're trying to do, and that is increase the usability and decrease the cost. But the theory behind it is well established, and there are actually enough proofs out there that show that a lot of the arcane protocols cannot work. They are impossible from a mathematical standpoint. There are proofs against them, and still we try again and again. And one of the reasons, of course, is because we hope, and the other reason is academia. But the real thing we would have to do is actually not develop another arcane system, but we have to fix the main problem, and the main problem is user experience. And part of that user experience problem is actually request-driven communications. It would be so much easier to have interest-based communication and anonymizing that than request-driven. And the reason for that is there's an expectation of response. So you make a request and you want a response, and that response has to fall into your attention span. And with a lowering attention span in the population, that becomes more and more of an issue. So you have to have less latency. In an interest-driven network, you have the information before you actually look for it. So that's something you basically out-optimize human psychology at that point. And that could work. But if you take the standard 3-second attention span that normal humans have, or worse actually, we actually run into a psychological issue that conflicts with privacy. So we have to change that. That part is the thing we have to solve.
Good God, man. I have not heard an explanation so clear and to the point on that. So you mentioned that, what was it? They're not the anonymity, no, the observability of links. So the current internet,
Yes.
as we have it, from ISP to every other ISP, we're completely aware of all those links.
Yes.
But from the ISP to
with a very few exceptions. So there are a few black
Sure.
holes out there, but
Sure.
let's say 95% of the internet, we know every single connection going on.
Right.
Like every UDP session, every TCP session, every ICMP repetition.
Yes. So now, just to sort of make a connection here, you mentioned that if you fundamentally have an interest-based network,
Mm-hmm.
with that, let's call it a concept. With that
Mm-hmm.
concept, you would be able to allow the very edge of the network, i.e. those individuals connected to the ISP, to be able to start connecting with themselves, not via an ISP. And then what would happen is that the observability...
No, they still need an ISP. They still need an ISP. Mm-hmm. But so what the difference between request-driven and interest-driven is that in okay. Request-driven, you have to travel through the whole network.
Yes.
You know, you have to gap a large distance. With interest, and you have to do that for every pair of potential receiver and potential requester. But with interest-driven networking, the distance is still the same for one request.
Yes.
But for every subsequent request, it becomes shorter. And it basically terminates on the edge.
So yeah. I understood that. So like, yeah, let's say you publish a blog and you're in the United States. I'm gonna my interest request thing is gonna go all the way across the world to find it and then pull back that data. And then maybe my next door neighbor, and I tell my next door neighbor, I say, hell man, this guy's written a good blog. And then when he wishes to get that data, the request or the interest is just going to come to me. And because I have a copy of it, it's not, it's not a cache system. It's not a cache system, huh? This data doesn't actually have a home because it's already signed. It's already, I can determine I can determine the provenance. I can determine the integrity and optional security. Well, security, not necessary, just the signature on this. And it would be copied to them.
Yeah.
Is that what you mean by interest?
I would make it a little bit less idealistic. There's basically what I think where the data ends up to be is edge -1. So it's not on your computer, but it's on the computer that the first hop that you and your neighbor share. That is where the data will be. So it's look at it as
understood.
Netflix, right? So how does Netflix actually work? Netflix works by having pretty huge storage and streaming servers at every big ISP on the planet. So and not just one per ISP, but basically one per city, and they don't usually have their whole catalog on it. you know. But what they have is they have the most requested shows, and they generate this most requested shows by two things. Number one, they know what is going to be hype soon, you know, and they can measure that in two ways. Number one is the marketing budget that they put into it. So if they put a lot of marketing budget into a show, they distribute the show to the edge everywhere. So because there will be a lot of people that just going to try it out, you know. And then the other thing is they actually know what happens in one time zone. You know, so they make a release, they see the interest in one time zone, and then they know, okay, we have basically this rate of requests for a certain show. It's likely going to be similar in another time zone where people are still asleep, they can't watch yet, right? So they distribute the stuff to the edge. So when people start watching, it is already on the edge. So that is one of the ways they can do it. And the second thing they do is the moment you are requesting a show from something like Netflix that is not on the edge, they will cache it on the edge, just in case that somebody else has the stupid idea of also watching the same show. And then the second one will have a better user experience, and their costs are driven down. It's not just about, oh yeah, there's no buffering, you know. It's also about their costs are dramatically lower if they don't have to deliver from the depths of their infrastructure, but instead can deliver from the edge of their infrastructure. Yeah. And it's the same thing. So imagine something like a Netflix type relatively intelligent CDN that is public use, that is basically operated as an open system. Yes, you're paying for it probably, but it's an open system and an open protocol.
Right. Okay. So this is okay. Now the next question I want to sort of lead. Okay. So this my question that I was asking a little bit earlier on assumed exactly this. So so with this concept of interest data or requesting for data, which can actually flood towards back to you and actually start to spread wherever there's interest, and they might have persistent, or even, you know, it could be least recently used buffers, right?
Yes.
So like the stale data, just wipe that stuff out. It's fine. And then now we solve the psychological thing. The thing is, like, how big a least recently used buffer do we need in order to maintain, you know, like the to go with the human psychology aspect? Okay, that's a heuristic we can tweak. So assume that we have an interest-based data network. Now what will happen is that we can now start to create links on the edge of the network. Now keep in mind, I might decide to pull a twisted pair from myself to my neighbor, and I don't even need that single hop. So I mean, I could start shooting lasers from my apartment all the way over to there, and then I know. It's now we start getting a little bit hacky over there, but assume this is the case. Like I could set up a rogue Wi-Fi network, which functions.
Wi-Fi 6 is the perfect choice for that.
Yeah. You see. So at that point now we start to lose the observability of the links, and this introduces a concept.
An ideal world.
Hey man, the fundamental technology is there, which allows it, you see, because currently, like TCP, IP, all of that stuff, it's difficult to do that. The technology, this interest-based stuff needs to be able to operate on like a broadcast network. Like currently, the problem is that we've got 99 receivers, 100 receivers, and only one responds and says, yes, that's my packet, you see. You want to have the technology such that everybody can look.
No. So I fundamentally disagree on that. So there are, how do you say that? There's an economic reason why the internet looks like it looks today. It's efficiency. So the network topology follows efficiency, and mesh networks are not efficient. Plus, they have a cutoff horizon after which they are too complex for anything. And the problem is that you basically have two issues in a mesh network. Like a realistic mesh network and not about a simulation. And the realistic issues are two. And number one is every link costs money. And number two is every link has to cross distance. And there's a thing with distance, and that is at a certain point, a direct link cannot cross distance anymore. So you and me, realistically, cannot have a direct link. There's no way of that. So even if we want, I mean, yes, if we were billionaires, we could have a direct link, but only one, you know? So at some point you have to share links. And that is you coming back to the internet, because the internet is about sharing links. And that is where the observability comes back in. Mm-hmm. Because the moment you have to share links, you have to deconflict links. And the deconflicting has to be done somehow. And it's the deconflicting protocol or authority that actually introduces the observability.
Okay. I
so
absolutely agree with you.
At some point fucked.
Okay. Right. Okay. I wasn't throwing the baby out with the bathwater and saying, okay, well, like I'm just going to use these rogue networks.
No, I'm a fan of rogue networks. So don't get me wrong.
I know that.
So I've done my quite share of rogue networking. You know, from laying fiber optics over a jungle in Panama, and reusing actually dark fiber on the Berlin subway.
Naughty boy.
Well, and you have to do something to make living worth it, you know. But a lot of these things are really interesting in crisis scenarios. You know, in crisis scenarios, a lot of these things are amazing because our usage patterns actually change. You know, then it's about, you know, I want to get these 100 characters to my friend to tell him that I'm alive, you know? So, and that we can do. But surfing the internet, going to booking.com, watching Netflix, whatever, those are usage patterns that are completely incompatible with that kind of infrastructure. So, and the other thing is like, when it comes to discoverability of data, when it comes to storage of data, when it comes to pre-processing, et cetera, all of these things make a lot more economic sense if they are running on specialized nodes that serve multiple people. Because you don't have a constant request rate as an individual, but you have peaks of interest and peaks of usage, etc. And to be efficient, you kind of want to harness the moments between the peaks, or you want to reuse the data between the peaks, or you want to reuse the data of the peaks. So, and that is why it makes a lot of sense to have things removed from the direct, actually, edge -1, you know, or edge -2. And it's actually every hop basically doubles the nodes that you're serving, more or less. So I mean, on the current internet, it's actually more extreme. So the first hop is like a factor of 100, and then the second hop is maybe a factor of 4, and the third hop is a factor of 2. But so the increase of use goes down logarithmically, I think. Depends a little bit on how advanced the area is in which you are living. So in Africa, it's not logarithmic; it's more or less linear in most parts of Africa. But like in highly developed nations, it's logarithmic. So and that makes a lot of sense because it means that it costs less and less money. You know, with less investment, you're creating more usage for more people. And in the end, whatever systems we build, we have to not just set them up, we have to maintain them, we have to keep them secure, etc. There are costs involved with that. And that has to be, usually when we run simulations of how great our mesh networks are going to be. All that doesn't matter, because it's not part of the simulation. But in the moment you roll out stuff in the real world, things change dramatically.
I couldn't agree with you more. Like, all of these rogue networks, they seem to fail. Well, the economic side of things, you can't just do it on goodwill, right?
Yes, and you have bandwidth limitations, etc., 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 that
indeed,
outcompete those networks unless you're really in a crisis situation.
Yes,
and the economics change during crisis; they don't change during normal life.
Yeah. Although, so the way I'm sort of going to try. Okay, look, this is all attempted hacking, and literally, it's just me sort of kind of having fun, but in a serious fun sort of way.
Sure.
My rationale was behind this is that, okay, moving old people's data in the case of crypto hippie is not valuable enough.
No,
the data.
That's why we're broke.
Yes, that's exactly it. But so what? Okay, now let's. This can be a very polarizing thing that I'm about to bring up, for especially in technical circles. But like, some might say that like Bitcoin data is actually some of the most valuable data, especially the transactions. It's important to you. It's a representation of your value that you are sending across the world. So then, if one makes, like, for example, Bitcoin transaction to be first class, that's the reason why this network is here, is to secure these transactions. Then you can sort of like, hitch your pony to that cart, in the sense that the community that would likely pick up this technology would be, libertarian, sort of like, people who want privacy and all of that sort of stuff. They see validity in this, and it's a market for them. And maybe what with the extra purchasing power they've got, they would also look into being able to create these non-observable links on the very edge of the internet that exist between them, and maintain those links, because any data that gets routed across that thing could incur a cost. So this now introduces this fundamental, like, economic model, which could, very slow at start. I'm not saying it's going to be like a huge thing, but it fundamentally can start the early stages of something growing and being independent.
Yeah.
What's your opinion on that?
Let me shoot back at that.
Please do.
So for value to exist, you have to do two things. It's not just the usability or the use function that is important. Like how valuable is the data for you? That's not really what determines the price. It's also the availability that determines the price. And
that's true.
And when you look at something like Bitcoin blocks or transactions or whatever, they are widely available, and that makes their price near zero. So it's the wide availability. So that is why I said before that crisis changes economics. So crisis changes the economics in favor of something like rogue networks, mesh networks, etc. Because then what happens is that the data has still its usefulness, but its availability goes down, and that is where the price for the data goes up. So then it makes sense for that data to travel a super expensive network. But as long as the availability is there, you don't the price for the data is close to zero. It's really at the point where data becomes rare that it actually gains value in that model. So it has to be exceedingly rare already to actually get a price, because it's not a mass data use. So there's mass data use where it's not the rarity of the data that makes it expensive, but the the size of data that makes it expensive. So that's, for example, if you're looking at sensor data, for example, or if you're doing surveillance, the value of the data increases by its size. But for something like Bitcoin blocks, that is not true. It's nobody cares. Well, it's actually negative. If it's too much, the usefulness would actually go down. But so in when it comes to Bitcoin transaction data, it would only really come with a price if it already becomes exceedingly rare.
Okay, so
at the moment of crisis. So if there's censorship, etc., etc. And then the question is also that yes, you would have value attached to that data and to its timely delivery. It's not just the existence of the data, but it's the timely delivery of the data. But then what also happens is that you are running into a scenario of competition. So there are various ways in which that data could reach you at different prices. And these are not just monetary prices. There are things like reliability. There are things like availability of the technology itself. There's things like risk exposure. If I'm caught using that technology, keep in mind, we're talking about a crisis scenario. What is the risk of me being caught with this? So these things come into the game as well, which my guess is, and actually the experience of smuggling a lot of data over the last 20 years.
Yes, the real smuggler is here.
Is that you almost always find a way to communicate if you always find a way to communicate in a way that is less suspicious. And the less suspicious ways of communication are usually the most efficient ones. There's a reason why there's so much research into stuff like
stenography,
covert networking, and delay and disruption tolerant networks, and data mules, and all that stuff. Rogue Wi-Fi, dead drops, and temporary exfiltration infrastructures, which is where I come a little bit from. And so it's almost always possible to move data. There are very few scenarios in which that becomes hard, and usually it only becomes hard at the borders, so to speak. So when you look at Kazakhstan, for example, so in Kazakhstan, the issue is that basically there's a handful of routers sitting in the capital city, and if you disconnect them from power, there's simply no global internet. But what still exists is local internet. So yes, they have this issue of having a very star-shaped infrastructure, but in most other cities in the country, you can have local connections over the existing internet infrastructure, because that is actually one of the things that the internet was built for. You can locally communicate even if the rest of the internet doesn't exist anymore. So if you're in the right city, you can everybody can happily share files and do everything over their existing DSL lines, because as long as you're not connecting to something where there is no connection to anymore, you're happy, So, and the problem is that, of course, our data consumption is distance oriented. Most of the data that we consume comes from very few points that have a large distance from us. And again, it's an argument for interest-based communication. It would be enough to get this data to a certain city once again, and then it will be available to everybody without the need of mesh networking. Because in the end, we already have this very resilient networking infrastructure. The problem is that it's the long links that get cut in a crisis. It's not the short links that get cut in the crisis. And the short links are the expensive ones, but they're already there, you know? And the other thing is that observability on the short links is usually not very established. So the communication between two clients of the same ISP that do a direct connection, there's almost no view on that in most countries. You know, it's the getting out of the city or getting to the IX or getting across the border is where the net flow is really tracked. You know, but you know where intelligence and secret police and whatever look at it. You know, but these little you're sitting on one side of the city, I sit on the other side of the city, we're using the same ISP and we're communicating with each other. That is usually undiscovered data. So and we can use that, you know, we can use that fact of the existing internet infrastructure in all of these scenarios. And just to make a counter argument again against the against replacing that with whatever Wi-Fi links or whatever, is yes, they become economic in a crisis scenario, but in a crisis scenario, a different thing becomes economic. And that is the deployment of physical resources by your opponent. And that means today that you have a high-flying drone with sticking capabilities over your cities. And that thing captures every single Wi-Fi connection. And then you're actually doomed by using a network like that, because then we actually know exactly where to send the hellfire.
Dude, I was right about you. I'm super happy I got this conversation with you, man. It's really, really interesting so far. Okay, so just to go back a little bit regarding the data valuableness, whatever
value, just value.
The data value. Yes, exactly. So justifying moving the data over an expensive network. So the thoughts I was having was actually it would be Metcalfe's law in the sense that you can actually send transactions to each other over something like Lightning. So you would implement Lightning on top of this. So this makes and let's just open that up anyway. And this makes okay. Remember that in the current internet, we have a separation between the name, the human readable name, and the IP address. And as a result, what happens is that it promotes data dissemination monopolies. So it's much easier just for you to, put your blog post or on Amazon servers or your photographs on Facebook servers, because they become the data dissemination monopoly in that sense.
But not because of their addressability.
Did you say not because of the addressability?
Yes, that's not the reason.
No, that's not the reason, because what happens is you create a point, because I believe, you can probably shoot me down, because of TCP/IP, we've got a point-to-point communication system, which means that in order for data to be communicated between me and you, I have to create a channel. And now what happens is that you create n communication channels between myself and Facebook. It's much easier just to go create one channel to Facebook, and Facebook has optimized the fuck out of its system,
exactly,
and via VC money and funding themselves by selling all your data to the government, which is printing the money and keeping their little like who's the author of Animal Farm? George Orwell's dystopia in full swing, right? So it's just easier to do that. And as soon as you reduce that so that like data is actually bound to the public key, and routing, it gets routed to you, you remove the rent seekers, you remove the ability for Okay,
I
shoot
think
me down.
I think there's a non sequitur in there. So yes, you're right. So it's more efficient to have less links. So that's the way you get decentralization.
Yeah,
is by concentrating links into hubs. So the bigger your hub is, the more use you have to connect to the same hub.
Yep.
That is network effects.
Yep.
So if you only have very few links to random people, the value of those links is relatively low, while the cost is still existent. But if you could connect to one hub that works most of the time, that's a condition basically, and that connects you to a lot of other people, that means that the amount of links you have to directly create while still having the profit of being connected to a lot of people goes up. So your link cost goes down while still having the usefulness of the whole network. And that is where you get a centralization from. And that is always the case. So I think the mistake that we often make is we think, oh, we create those networks that are permissionless, everybody can participate in them, hence they will be decentralized. But that is not true. Given the normal environment and normal economics, you always get centralization. You don't get centralization in a single point. You usually get centralization in 2 or 3, sometimes 5 points. And the reason for that is twofold. Number one is competition in usefulness. So if you have multiple players on the market, they start competing with each other, and their hubs become more useful or less useful over time. And so people kind of connect to more hubs or focus on certain hubs based on their needs. So you usually have at least 2 players in a system. And the second thing that happens is that because no system is perfect, you have failure. And people select usually more than one to be able to survive failure, or markets select more than one to survive failure. So, and that means that in most systems you have these 2+ nodes, but usually like central nodes, but it's usually 5 or less. So you can actually look at a lot of organically grown networks on the planet. You can see that in organizations. You can see that in industry. How many players do you have in a certain market, et cetera, et cetera, et cetera. And it is usually this model that is 2+, but smaller than 6, and that goes everywhere more or less. It's even true for things like connections to watering holes. Where does deer go to drink? You have a similar distribution, and
power laws.
Yeah, because you have like mating strategies that are connected to that, et cetera, et cetera, et cetera. So the world basically thrives towards weak centralization. So it's not strong centralization in the sense that it's one point,
I see.
but it's weak centralization in the sense of there are a couple of points, but it's a handful basically.
Yeah, economic forces and efficiency in
yes.
ideal sort of peaceful times
yes.
drive this. But as soon as you
yes.
said there's a calamity or something, then it can
right.
decentralize.
Crisis changes things.
Crisis
changes things mostly because the territory of operation gets fragmented. That is why crisis changes everything.
Yes.
So, and then you basically have the same kinds of distributions that spring up in those under territories. So, and yes, of course, you have the total number of nodes goes up, but the layout is still the same, because when you look at all kinds of networks, they're basically fractals. So if you look at a map of the internet, not just where the links run, but peering relationships, etc., etc. Those are fractals. They have self-similarity. When you zoom out of them, you see those 2 to 5 big centers, and then, but if you zoom into the edges, you see those 2 to 5 local centers, and then you zoom in more, and then you see the 2 to 5 edge. Exactly. So, and that is how it's basically a fundamental of the world. There are very logical laws that drive towards that. It's the same thing with when you look at the Lightning Network. It makes a lot of sense to have a channel with big hubs because it allows you to make payments to so much more people easily.
Yeah.
It's the same thing. So there's a certain drive towards centralization. Or even if you look at a minor distribution, it's the same thing. There's an upper bound, luckily. So there's a physical upper bound that is determined by how much power you can get in a certain
region,
location. In that region.
Yeah.
Exactly. So that is creating an upper bound, basically. And that is the only thing. So it's an outside upper bound that is forced on the system that actually maintains wider distribution. And this, again, is the same thing as in the internet, because the cost of links and state borders and where do we have land links and where do we have to go underwater, et cetera, is the same thing that creates those sub-distributions. Otherwise, the world would be a star network, So, and so it's the same thing everywhere. And I think that it's that the smart person keeps that in mind. You keep in mind that there's a form of natural centralization, and that natural centralization is not necessarily an evil thing. It can be exploited in good ways, and it's up to us to exploit it in good ways. And that is better than wasting our time to start to or try to decentralize over and over and over again. And the only thing that we actually do is we waste our resources that would be required in us exploiting the centralization that already happens.
Right. So, okay, that's great. Now, to go to another point that I wrote down over here, you were mentioning as soon as you go into the interlink stuff across this observable network, well, you're fucked. So what if?
Well, you're fucked if that is the basis of your privacy.
Oh yeah, sure. Yeah. If that's the basis of your privacy, but I mean, like every practical network, it's a small world graph, right? You want to have these occasional long distance links. And those are the ones that are going to be snipped whenever there's a conflict or problems in the environment.
Yeah.
So how about in the scenario, I mean, given that they can be seen, so how about in the scenario whereby the long interlink is actually controlled by the enemy, but the connection that is made looks like an innocuous, I don't know, clear text HTTP or SMTP or something else. But what's actually happening is you're getting stenographically embedded packets that are actually going across this thing.
Yes,
that's an interesting thing, because I can create these little what I call links within my protocol. It's a separate concept completely. You can one router can have many different kinds of links. I could essentially create a stenographically supported TCP link, for example, or a SMTP link or something like that.
Yes.
That would contribute, would it not?
No, it would contribute dramatically. And there's another thing that makes that an interesting approach, and that is data consumption asymmetry. There's a huge asymmetry between the amount of data that we produce and the amount of data that we consume.
Yes.
So, which means that one of the reasons for that is most of the data that we produce is actually signaling data. Again, where we signal interest. So you go to a website to read the news. You're not actually communicating any formal data except for your interest. You're just saying, "Hey, give me that website," and that call is a couple of dozen bytes. Let's say it's 100 bytes. So that's all you do. And in the response, you get this 3 megabyte news site, So, and the interesting thing again is the interest that you communicated is actually shared with a lot of other people. So what you can actually imagine, and I think that is a thing to really explore in the future, is to decouple the routes even more. So right now on the internet, there's no guarantee that your route is stable. So the number of hops that you, or the hops that are between you and the target is a dynamic collection. And there's no guarantee that the same hops that you send the package over are also the hops that you receive the package over. That is one of the powers of the internet, actually. So, and when you're talking about interest-based communication, what you could actually do is you could use steganographic methods to send your interest over this widely accessible landline link, but that link is under threat, and then use something like satellite broadcasting to make the data available in your region. So it would basically drop down into your city, and then in your city come back to the links, because it's cached in your city. And so a combination of a little bit of Starlink here and a little bit of U-beams there, combined with steganography, that could go a long way if we are going away from this request response pattern that is end to end, and instead make it a subscription or interest-based pattern of communication. So that is one interesting thing. And one thing that I should actually throw in there to make that more understandable and more feasible is when we're talking about that, when I'm talking about data, I'm not just talking about static data. I'm also talking about code. So you can edge distribute code today because we have stuff like WebAssembly and stuff like that. So sending the program with the data is a realistic thing to do now. So, and that means that a lot of services can actually be edge distributed. I mean, there's a lot of work that needs to be done there. Let's be really honest. This is like we're talking about a technological change that, if successful, is going to make billions for everybody who's involved in it, and is highly interesting for VCs, et cetera, and will basically fuck with every current internet ecosystem we have. But it will actually be better. And it's actually realistic today. It wasn't realistic 20 years ago. Today it's realistic. Because advances in computing and hardware, et cetera. And now coming back to your steganographic communication, the thing is, if you have enough data that you can hide in, you can always make a provable, undiscoverable communication in it. So that's another thing that we know since Shannon, actually. So information theory goes a long way. You have to apply it a lot, but at some point you find this spot where it becomes low probability detectable or extremely low probability detectable, but it's still enough bits that you can transfer outside the compression window. So, and the funny thing is that the internet is actually better for that than a lot of other things, because we can transmit bits not just in our packages, but also by the fact that we're sending packages. We can transfer bits by the timing of those packages. We can transfer bits by order of packages, which is a natural occurring thing on the internet, is that the order of packages gets fucked up. And you throw in enough error correction and you can basically always exfiltrate data. As long as there is any link, you will be able to trickle bits through it. And that is exactly what a lot of people do. Like a lot of the advanced, how you call it, cyber espionage campaigns, etc. I mean, the data exfiltration is like one of the high arts in their field, and there is a shitload of things you can do that are almost impossible to detect. And actually, it's becoming easier. And so, because you said before, you would send clear text around. No, you actually want to send cryptographic material around because number one, it's the common thing, and number two is cryptographic protocols have so many parts that are required random that you can use to place data without it ever being provable that you placed it. So, for example, you can encode data into nonces. You can use stuff like wheat and chaff protocols to communicate bits. It's like, does a certain hash on a certain nodes produce a 1 or a 0 as a first bit? That's like the thing that you communicate.
Ooh, lots of computation there.
Yeah, but it's not that big. So if you're looking at modern computers that have stuff like on silicon hash generation, and you look at the standard nonce sizes in a lot of protocols, they just coincide with the block size of the hash, which means that it's two calls to the processor to actually process that. And your network card is actually able to do that. So you can actually offload it to your networking card, because that same feature is in a lot of networking cards, because we offload a lot of like routing decisions, security, encapsulation, decapsulation, even IPsec, etc. You can offload to better networking cards. I mean, your Ethernet card today is a computer. It's not just I copy something from the file layer. No, there's a computer and an operating system on it and everything. And actually, a lot of these are open source. That's the reason why we have stuff like PXE bootloaders and stuff like that. And there's a whole universe of how you can make interesting data suddenly trickle out of your card.
Fascinating. Yeah. Oh man, you got me so engrossed in that particular thing. I didn't have a follow-up question. No,
Sorry.
no. No. It's fascinating how you can take something and just expand on it. Let me think a little bit. Yeah. Oh yes, I remember now. Okay, so you were referring to actually distributing of code over this
Yes.
same network. It's funny that you mentioned that. So I'm actually using this networking protocol as the basis of a capability programming language, which is similar to back in the day. Mark Miller created something called E-language, right? Which is a capability-based domain-specific language implemented on the Java virtual machine. And he's done a lot of foundational work in the underlying cryptography of these systems. So now, imagine a world you've got a device which is rather similar to it's not easy. Oh yes, and a device that's rather similar to this that sort of sits in your living room, right? And
little Raspberry Pi,
yeah, something to that effect. And it's running a unikernel which only supports one process, which boots up a virtual machine, and this virtual machine executes a kernel language. This kernel language has good support for capability-based programming, and it pushes the concept of deterministic data flow programming to the very end. Now, what does that mean? That means that we can actually create these systems, these distributed systems, whereby every single variable inside the programming language itself is a data flow variable. So the entire programming language will continue. It's non-blocking. It's not blocking until a data flow variable gets fulfilled. And that data flow variable might be on the other side of the world in the form of this, using this protocol, which might have stenographic links. In between it. And it's all abstracted away. So you, as the application programmer, you actually don't give a shit about the security layer. You just write your program, your app as if it, as is. And every single time you want to call in code, like, you import code, you import a library into your system, you're actually using this cryptographic, this capability thing as a first-class citizen inside the language. So like public keys become first-class citizens. I can say I've got this closure, and I want it to be shipped, packaged up, and shipped off to the node that has this public key, the private key associated with it. And then it would just pull it across, and then just like, okay, it's signed. It passed the integrity check. I trust this code. I will now execute this code. And then it's sitting on that node, maybe in Panama, that you've got running over there. Man, that's an interesting new way of looking at things. Hey, but hell, it's a lot of work getting this virtual machine working. I'm working on it right now.
Yeah, I think one of the things you might actually be interested in is a project called WASM Cloud.
I want to stay away from anything to do with the web people. The web people fuck everything up.
It has nothing to do with web people.
Well, WASM is, WASM is all web people stuff, right?
Well, no. WASM is a portable instruction set. That is all WASM is.
Yeah, but it doesn't support tail call optimization. I need that. I need tail calls. Sorry, bro. I need tail calls.
Okay, whatever. Okay, but the interesting thing is, one of the things that they do is they have a call fabric where you can have different pieces of code that basically use a call fabric. So basically a contract is a cryptographically secured contract that interlinks those pieces of code. So you can basically push a WASM file into one of those clouds, basically. And that WASM file can tell other WASM files, hey, I'm providing a certain service, and this is my proof that I am allowed to provide it. And then these different WASM objects can call each other and run against each other, and including interfacing for networking, et cetera, et cetera, et cetera. So what you can do is actually have these. So again, it's the foundation is message based infrastructure, where you basically take the technical addressing away and make it into a semantic addressing, an interest-based addressing, and then have a proof of authorization attached to am I allowed to consume it? Am I allowed to produce it? Whom am I allowed to send it to? From whom may I subscribe it, etc., etc. So you have this fabric of very, very small bits of code that are living in a substrate, so to speak, where they can talk to each other, but they can make sure that they're talking to the right other piece of code. And then including stuff like being able to automatically or dynamically change an environment like that, updating very small modules out of this fabric, replacing them on the fly during runtime in a globally distributed manner. So it's not a single computer. You run it on hundreds of computers, and including stuff like the code moves to the computers that have most resources available and stuff like that. So you have rebalancing. So that is
work stealing.
I think yes. So it's for sure a direction in which a lot of thought goes right now. It's like the direct link between computer and code, or code and communication, is going away. So we're more and more moving towards this thing where code is an abstract entity within a network of communication, and that is especially interesting because we're Java 20-30 years ago however long ago, made this promise. You can code something and it runs everywhere. But the thing is, we are actually accomplishing that right now.
Yeah.
And it's one of the conditions for such a. I don't even have a good name for it. It's like fog. Let's call it fog computing. So it's one of the conditions of this fog. And there's an interesting aspect to it, and the like historically interesting aspect, and that is when you look at the ideas that were floating, like the cypherpunk mailing list in the late 90s. One of the big concerns of the cypherpunk was always tamper resistance, tamper evidence, and attestation. So how can we run code and trust it? So even if it runs somewhere else, how can we trust it? And there was always like one of these big dreams was to be able to take a piece of code and maybe not even reveal it, send it somewhere else, have it executed, and be sure that it is actually executed correctly. And today we try to do that, like with homomorphic circuits and stuff like that, and I'm relatively skeptical there because what the fuck. Anyway, but there's another thing, and the other thing is that trustable and attestable computing is actually a thing that is beginning to exist right now, and the reason for that is the fucking cloud providers, because everybody is moving everything into the cloud. The cloud has to provide trustworthiness. And the only thing you can do that is actually by building all your processor infrastructure into a trustworthy computer. And the thing is, those processors are not just sitting at Google, they're sitting under my desk, And then things like, I find it fascinating. It's still work in progress, and there's a lot of security issues still. It'll probably need another 5 years. But look at something like modern AMD processors. EPIC, for example. So what do you have in EPIC? In EPIC, you have TPM hierarchies that allow you to do attestation of the whole call stack from the first bit up to the kernel in your virtual machine. So it's not just the host operating system that you can attest the virtual machine. And you can transfer keys between TPMs and different computers so that the keys only become unlockable if the attestation chain on the other computer is valid. So you can actually transmit secrets that only become available on the other machine if the other machine has exactly the characteristics that you pre-computed. And you have stuff like on CPU, on die RAM encryption. So so basically the only unencrypted data that exists is the data that is on the registers and in the cache of the CPU, and everything else is encrypted. So all that part is on the die, and the die itself is observing itself for tampering, and tampering detection will undermine the attestation chain, and the attestation chain basically blows up your VM there. So in theory, at least, yes, there are implementation issues. It's a lot of the code that is used there is it's not the quality that we need. But on the other hand, I think it's very realistic that we get the quality at some point, because it's a well enough describable problem, and it's small enough that it actually makes sense there to use provable programming techniques, to actually prove that the code is according to specifications. And we will sooner or later have that. We will sooner or later have a trust stack that is completely proven. From the first bit to the last bit will be completely proven, and it will incorporate things like unclonable physical functions that will actually make it possible for us to detect if we're running on a real computer or in a simulation. and stuff like that. And that will allow us to have movable code and movable data that no matter where on the planet it executes, we will be able to trust it and it will stay secret. It will be unmodifiable and it will not leak any information. And that is a thing that, in my opinion, will hit within the next 2 to 7 years. We will have a basis for that. And that combined with something like, interest-based communication will change everything fundamentally. We will not talk about individual computers anymore. We will talk about something like computing commons, maybe, that you pay by demand no matter where they are on the planet, and they will move to where they are needed and not where they are currently hosted, So, and that will happen. And the other thing that an infrastructure like that also allows us is actually to make real micropayments between those systems possible. So right now, doing micropayments is impossible to do in a trust reduced way. Forget about trustless. There's no trustless. There's only trust reduced. So doing micropayments in a trust reduced way is currently completely impossible. But the moment we have a publicly attestable infrastructure, like cryptographically attestable infrastructure, we will be able to do those things at a very, very cheap price. And it will open up protocols that we cannot currently implement. And then we're probably fucked as well. I'm not necessarily saying that's going to be a utopia. We're probably going to come up with a really good way of making that into something terrible. But it's technologically interesting.
So those are the unknown unknowns, right?
Yes, exactly. Always keep them in mind.
Yes, yeah, they're out to bite you, man. That's what they do. So, exactly. So you mentioned like a TPM infrastructure. Now, I'm circumventing this to the best of my ability. I really, I did the whole looked into the hardware sort of thing, and I'm like, okay, I'm going to have this little dongle here, and everything's going to be from this point downwards, I'm going to be able to have the entire thing, attestable. And I was like, fuck, I don't think I can take this battle, given that I want to implement the virtual machine and et cetera, et cetera, et cetera. Right. So I thought, just go with a unikernel.
Yeah.
And then distribute that as assigned with maybe my key, and then you just flash it to your device and you run it.
Well, that is of course something that it works as long as you have physical control. And the physical control is this very specific thing, because it doesn't really mean it sits in. It not only means it sits on your desk, but it also means that you glue it together yourself.
Yes.
And so, but again, it's like most things, it's a probability game, So if you can have 100 of those nodes and only one is untrustworthy, that might be fully enough. We often have these very theoretical standards of how secure something has to be. And those standards are usually unaccomplishable. But in most cases, probabilities are enough. It's like in most cases, like 50% plus 1 is enough. So or 50% plus the number of computers that might break in the next week, is enough. And I think that it's something to remember from time to time, because we often over-engineer the shit out of stuff to reach theoretical limits that, number one, we will never reach, and number two, we don't really need. So that's another thing. We actually never need certain standards, and then we waste a shitload of time and everything to implement stuff that then fails to achieve them. So I think there's as always, there's a gradient to all of these things. It depends on what you are running on it. whatever. I mean, if you're running an HSM that is controlling 50 billion US dollars, yeah, your security shall better be secure, you know. But if it's about sending dick pics around, it's probably not that important, you know, like unless you're David Beckham or something, you know, then it becomes expensive. So, and that has to be kept in mind whenever we're building systems. You know, they have to stay realistic and usable and payable and all that. And yeah, that's there's space for a lot of creatures in the digital ecosystem.
Oh, tell me about it. So you can start to feel like there's an element of familiarity between us growing now, and you know, there's also an element of tiredness that's sort of happening now. It's just been very intense conversation. So I just want to sort of run down this conversation with one sort of like last sort of question. What sort of future things do you see, future technological trends that you sort of see might be of interest, that are of interest to you, that you're quite optimistic about? It's, you know, yeah. Is there anything else? Sort of
Well, I don't know, because every second day I wonder if I should leave computing and become a farmer or something.
Oh, tell me about it. Tell me about it.
I don't know, and I have the feeling that everybody who's been in the game for more than 10 years kind of has that thought all the time. So we might have a very unhealthy relationship with our jobs. Maybe I should go into psychology. Never mind. Technological trends. Yeah, one of them I already mentioned. So global publish subscribe infrastructure, interest-based communication. I think that's going to, it's the right way to go, and I think it will happen. The other thing also mentioned already is mobile code. If trustworthy or not, execution doesn't really matter for a lot of use cases. Because parallel execution in different trust domains is enough for most cases. And then basically you just attach a cryptographic proof from time to time, and then you're happy, you know, you don't need much more, you know.
Yeah.
So as long as you're not controlling the Fed, it's good enough security. I think that trusted computing is something to keep an eye on, because especially because of the forces that all the cloud computing, but also mobile phones are creating. You know, so the mobile phone security is introducing a lot of interesting aspects. So stuff like open source hardware root of trust systems are a fascinating aspect to look into.
Vault 1317, are you familiar with that?
No, I'm not.
So there's a hardened Linux project.
Okay.
Sean Chang, he's number 7. I've interviewed him number 7. He's one of my good mates. He's part of we've got a man cave out here. You know, it involves cigars and lots of whiskey and a hell of a lot of shit talking, man.
Yeah, I can see that.
Actually, I think we got one probably coming up next week, and it's going to involve a jacuzzi. Oh yeah.
So I've heard worse.
Well, we're this is a public talk, right? So and he's doing a lot of this attestation stuff. You know, he's got a thing called Vault 1317. And he's looking at that. You know, he's the founder of the hardened Linux project. You should probably know.
Oh yeah.
So okay, so
so I find that development fascinating. So I mean, you know about Graphene OS, right? So
please repeat. I know about what?
Graphene OS.
Graphene OS. Yes, continue.
Yes.
But there's also there's a fight between, is it Copperhead OS or something?
Oh, that fight is long over. So it's like
so annoying.
Come on. Yeah. Hey, it happens. You know, you take two smart people, you put them into the same room. Sooner or later, they find something
Cat fight.
to fight over. It's normal. So I don't know.
Okay, keep going.
But,
Graphene OS.
one of the things they really did is making your system remotely testable. Like having an Android phone that is remotely testable, where you can actually, or even with a second phone, locally testable, where you can basically have assurance that your system is not compromised in the early stages. And those are things that that an open source project does that and makes it widely available to people is an interesting change. And I think stuff like that will show up more and more, and that will change a lot of security assumptions. It will change a lot of assumptions that we can make about how to create systems. So it's a thing to look at. Another thing that I think is really interesting and will have an interesting will change interesting things is satellite internet. So the various constellations that are coming up there right now, especially when you keep in mind that they're built for in-space messaging, so that they will route a lot of the traffic in space instead of just being a bent pipe.
Yeah, but that's dependent on Elon Musk, and he's pretty well known for being a bit of a scammer. That guy.
Well, it's not just him, It's like a couple of constellations going on. So, and the interesting thing is sometimes you need a scammer to wake up the market, because everybody else thinks that they have to compete with a scammer, and then you get your shit anyways. I mean,
dude, go into psychology, man.
So if I find that interesting, there might be interesting things, but I think that actually one of the, like, when it comes to fascination, what I find extremely fascinating is certain legal changes around how to do data shit. So, for example, what I'm super fascinated with is this development of cyber embassies, where you can basically, as a state, create a data center in another state and declare it extraterritorial.
Wait a second, what is this?
Well, exactly. And that is a thing that has now happened like 3 or 4 times. And there's like a country that has become a provider for stuff like that. And I'm kind of thinking that give it a few more rounds and other countries will realize that selling their sovereignty to data centers is actually an interesting business. And that will fuck up a lot of things.
Have you ended what you were going to say? Like, where's the explanation? Like, so give me more details. Okay, so how is this? So which country is allowing these sovereign sort of
Luxembourg?
Oh, is that so? Okay.
Yes.
So all of these. Okay, let's call them digital citadels. Let's call them citadels. Okay.
Mm-hmm.
Bitcoin. And then so these citadels have been registered in Luxembourg, right? All 3 of
them. So basically, what it means is that a country like Estonia, that is like very digitally focused, blah blah blah, and they go to Luxembourg and say, "Hey, we want a piece of a data center, and we'll declare it Estonia." And
but that means Luxembourg will only recognize what registered countries, right? According to
right. So it's basically all based on extending like diplomatic rights to infrastructure.
Okay.
So and Monaco has done the same thing. They moved the data center into Luxembourg and declared it Monaco. And the interesting thing is, if you think about it, think about a big data center where you have like a cage for the US, a cage for China, a cage, and they're basically next door to each other. And that is a potentially really vile thing that can happen there. And that's something that, you were asking for things that I find interesting or to look at. It's one of the developments I strongly look at. I think they might accidentally create scenarios that we can exploit. And I will always help them to create those fuck ups. So
Well, as the real smuggler says, I mean, surely smuggling data between those, just like within a data center, it suddenly becomes a lot easier. Is that right?
yes, potentially. And it also creates these crazy things that you suddenly not only have multiple jurisdictions in one data center, but they're also creating jurisdiction-less spaces out of necessities. Because it's common infrastructure between multiple jurisdictions, so they become basically anarchic. So, like all of the world system really is, I mean, the system between states is anarchic, and if they that is something that might actually be really exploitable. So imagine you have something like mobile code that switches between the US, China, Russia, etc., with a latency of 1.2 milliseconds. Right? So, and that is something that I find highly interesting.
So no, let's further this use case. Like, what could one do with that? Okay, now you've got this latency drop massively. What would you do with that?
Well, it basically means that you're breaking below the threshold that you know for localization.
Yeah. So basically, there's a whole bunch of stuff. It's a whole new world.
It's a whole new world. It basically means that you can run code that cannot be located to your jurisdiction at any. You cannot link which processing step has been happening in which jurisdiction.
I start to appreciate what you are saying now.
Yeah, and let's not talk more about that.
That's
it's
fine.
An exercise for the listener.
That's oh, next subject. Dude, that's a very interesting. Okay, I'm glad you mentioned that. I'm glad you. Oh, dude, do you have anything else like that?
No, I have to keep a few things for myself.
No, that's fine. That's okay. Jonathan, it's been absolutely wonderful. It's very rare to find somebody with such a deep knowledge of the internet and the workarounds and all the problems associated with it. Like every single question that I've thrown at you has come back with like high signal. Very rare to find us. I'm glad to have made your acquaintance.
Thank you. It was fun.
And next time I'm in your part of the world, I expect we're going to have a beer. I expect it.
No, I think you promised me jacuzzi, whiskey, and cigars.
Well, sir, I've got the right gang, the right sort of people you'd just love to hang out with. So next time you're out in Hong Kong, look me up, man. We're gonna go in that jacuzzi, whiskey, and there'll be a whole bunch of other vices there too.
Beautiful.
Okay, let's wrap up this thing now. I'm just gonna stop recording.